This is Dr. D. Govardhan, Professor in Head, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, we are discussing shear force and bend moment diagrams for the cantilever beam subjected to gradually varying load in mechanics of solids. Whenever a beam is subjected to vertical loads, it always deflects or bends due to the action of the loads. The amount of which the beam load bends, generally it depends upon the magnitude of forces which are acting on it, length of the beam, elasticity of the beam, and type of the beam. The vertical loads which are acting on the beam, generally it is considered as shear forces. Here the word shear force is representing the unbalanced vertical force which is acting on the beam, considering with respect to the point toward the right side or left side of the section. Bending moment. The bending moment at the section of the beam is the algebraic sum of the moments created by all the forces, considering to the right or left of the reference point of the section. Different types of loading on beams. Here, several types of beams that loads are acting on the beam, but here we are considering the important types of loads are point load. It is also called concentrated load, uniformly distributed load. Sometimes it is also called UDL, uniformly varying load. Apart from these three loads, it may be consist of a combination of point load and uniformly distributed load, or point load, uniformly varying load, or it may be the combination of uniformly distributed load and uniformly varying load. Point load or concentrated load. A load which is acting on the beam at a point is called point load. It is also called concentrated load. Uniformly distributed load. A load which is spread over a beam in such a manner that each unit length is loaded to the same extent is known as uniformly distributed load. Generally, it is represented as omega kilonewtons per meter. Uniformly varying load. A load which is spread over a length of the beam in such a manner that it varies from one end of the beam to the other end uniformly is known as uniformly varying load. Sometimes the load is 0 at one end and increases uniformly to the other. Such a load is known as triangular load. The uniformly varying load is also called UVL. Sign conventions. The sign conventions for the shear force and bending momentum is most important. To determine the magnitude of shear force as well as the bending moment acting at a given section. Shear force. The word shear force is generally it is the unbalanced vertical force. It may be considered toward the left hand side or right hand side of the reference section, and generally the acting upwards or downwards depending on type of the beam. Now, here example we are taking simple supported beam AB. It is subjected to 1000 newtons as shown in figure. Here this force 1000 newtons is acting vertically downward directions but the reactions RB is acting in upward directions. That means these vertical forces may act upward directions or downward directions. The shear force is considered as positive when the resultant of that force to the left hand portion tends to slide upwards, or the right hand portion tends to slide downwards. Similarly, the shear force is said to be negative when the left hand portion tends to slide downwards, or the right hand portion of the beam tends to slide upwards. In other words, all the upward forces of the left side and downward forces to the right side are treated as positive shear forces. Here example, here the cross section XX is there now. With respect to the XX, the forces which are acting downward directions, that is 1000 newtons, is treated as a positive shear force. The reaction force RB is acting upward directions is treated as a negative shear force. Similarly, toward the left hand side portions, here RA is acting upward directions, so it is treated as a positive shear force. Bending moment. At a section where the bending moment is such that it tends the beam at a point to a curvature having concavity at the top, as shown in figure, is treated as a positive bending moment. This effect is also called sagging effect. It is in the form of U shape as shown in figure. Negative bending moment. When the shear force is acting on the beam, it deflects in such a way that its center of curvature having convexity at the top, here as shown in figure, then the bending moment is treated as a negative bending moment. The effect of convexity at the top is also called hugging effect, and generally it is in the form of inverted U shape as shown in figure. Now today we are considering shear force and bending moment diagram for a cantilever beam carrying a gradually varying load. Here a cantilever beam, it is a beam in which one end is fixed, other end is free as shown in figure. Consider AB is the cantilever beam having length is equal to L as in figure, carrying a gradually varying load 0 at one end, that is at B, and gradually varying in such a way that it becoming W per unit length run at the fixed end as shown in figure. That is here at this position. That is nothing but it is changing W per unit length run. That means at the middle now, just somewhere if you take at X position now, X position, I am taking it is in the form of here triangle position now. This is treated as the length of the beam. Here it is given omega now. At a distance of X when I am taking, that this height is required now. It is called here now the load acting at this moment. Here it is given by, because it is varying W per unit length run. So at this moment, if the distance is given X now, these two are now treated as here one triangle and it is one more triangle. That is, if I take A, B, C, D and E now, that ABC as well as the DEC both are similar triangle. This height is equal to, it is given by the load, it is equal to, we can take it as WX is equal to, it can be written as W by L into X according to the similar triangle principle now. So the load which is acting at any position now, it is given by that height. It can be measured by using the relation Wx is equal to or omega x is equal to omega divided by L into x now. Now let Fx is representing the shear force at the section x now, and Mx is representing the bending moment at section x. The rate of loading at x from the end B, this is called rate of loading at a distance of x from the free end. It is given by W into x divided by L. So the shear force at a section x at a distance of x from the free end B is given by, that is nothing but, here the shear force is nothing but, according to our definition, it is the unbalanced vertical force that is acting with respect to the given point. It may be toward the left side or the right side now. So here I am taking when toward the right side. This is the treated as unbalanced force which is acting now. That is the area under this curve. It is treated as the load which is acting. Here it is given Wx divided by L. Here it is 0. It is in the form of in the triangle. Hence, the load is equal to, it given by W into x by L into x divided by the 2 now. That is the area of the triangle now. So, the shear force at a distance from the x, from the free end, is given by W into x divided by L into x by 2, or it is also known as W x square by 2L now, or it is the area under this curve now. Here the minus sign, here it is there now. Since it is acting here in downward directions, hence the shear force is treated as a positive now. Then the shear force is 0 at free end, that is when x is equal to 0, and increases in the form of parabolic curve, because here if you observe this equation now, the shear force is nothing but at any section x from the free end is proportional to the square of the distance. Hence, it is varying from B to A in the form of parabolic curve. Hence, you have to take here 0, find the maximum values here at, which is equal to, that means x is equal to L when we are substituting. The shear force at A is equal to WL square by 2L, which is also equal to W into L divided by 2 now. So, we are taking WL by 2 now. You have to join here one point to other point in the form of parabolic curve. That is the way of just drawing shear force diagram. First of all, draw the cantilever beam according to the suitable scale, and draw the vertical lines to represent the length of the beam. Take the length of the beam as the axis. Take 0 at one point. Other point is equal to WL by 2. That is the load which is acting. Just join these 2 points by smooth curve, isosceles figure. This curve is called parabolic curve. The bending moment, first of all, we have to determine the bending moment at a point to x from the x distance from B point as shown in figure. The bending moment, it is equal to moment created by the shear force from the left hand side, right hand side of the section now considered, hence which is equal to mx is equal to the load into distance is required. That is, load is equal to at x distance is equal to W x square by 2L, already be determined from FA. But this force is acting at its center of gravity now. Hence, this force is nothing but here the force where is the constant center of gravity of the triangle. That means from the base, it is at a distance of x by 3 now. Because the total force is equal to Wx square by 2L, but it is acting at a distance of x by 3 from its base. That means from this distance you have to determine. So the bending moment is equal to, it is the product of force multiplied by the distance between the point where the force is acting to the reference point. That is x by 3. So Wx square by 2L into x by 3, or in other words, it is equal to Wx by x cube divided by 6L as shown in the equation number 3 now. So here now, the bending moment is proportional to the cube of the distance from the free end to the reference point. Hence, the obtained curve is known as a cubic curve. So here at A, the bending moment is given by Wx square by 6L. Since x is equal to here now L, on substituting we got WL cube by 6L, which is equal to WL square by 6 now. So just to draw the length vertically in downward directions, which is representing the value of WL square by 6 according to the suitable scale, and join B with this point by using smooth curve. This curve is called cubic curve. Okay, this we are taking certain problems based on uniform gradually varying load. A cantilever length of 4 meters carries gradually varying load 0 at the free end, 2 kilonewton per meter at the fixed end. Draw the shear force and bending moment diagrams for the cantilever. The given that in the problem is a cantilever length of 4 meters. That is, the length of the cantilever is equal to 4 meters is given now. And carrying gradually varying load 0 at the free end and gradually increasing load, varying load, and finally it becoming 2 kilonewton per meter at the fixed end. So here it is equal to 2 kilonewton per meter now. So W is equal to, we can take it as a 2 kilonewton per meter now. So the shear force diagram as shown in figure, it is representing, it is a B, in which the shear force at the fixed end FB is equal to 0 now. Similarly, the FC is equal to, that is the shear force at the fixed end A is given by the area under this triangle now, which is equal to W into half into W into L now, or WL by 2 now. So which is equal to 4 kilonewtons. So this 4 kilonewton you can take, just you have to draw these two lines by smooth curve. This curve is called here parabolic curve. Similarly, the bending moment diagram. The bending moment diagram at the free end is equal to 0 and at the fixed end is equal to, here it is required, that is M into A we required, which is equal to total force required. Total force is equal to how much it is now? Here W into L by 2 required. W it is there, L by 2 or area under this triangle now. But it is acting at a distance of from the fixed end, its center of gravity. The center of gravity of the triangle lies at a distance of h by 3 from its base, or L by 3. It is equal to, you can take it as L by 3 or WL square by 6 now. By using these relations now, we got to 2 into 4 square by 6. It is equal to minus of 5.33 kilonewton meter now. But the effect of this bending moment, it deflects the beam in the form of inverted shear. It is also called convexity at the top. or the effect is also called hacking effect. It is treated as negative. Hence, first of all, in order to draw the bending moment diagrams, from B, draw one line now. From A point, draw one more line to represent the length of the beam. Take horizontal lines. Here at B is equal to 0. At A is equal to draw vertical lines in downward directions to represent 5.33 according to the some suitable scale. Assume here the suitable scale is equal to 1 kilonewton meter is equal to 10 mm now. That is, we can take 50.33 and join these 2 points by smooth curve. That curve is called here now cubic curve now. This diagram is called here bending moment diagram for the cantilever beam when it is subjected to gradually varying load. The second problem. A cantilever beam 4 meter long carries a gradually varying load 0 at the free end to 3 kilonewton per meter at the fixed end. Draw the shear force and bending moment diagram for the beam. Okay, the given that in the problem is a cantilever beam of 4 meters long. That means the length of the beam is equal to 4 meters. And the load at B is equal to 0 is given now. That means the shear force at B is equal to at fixed end is at free end is equal to 0. And gradually varying to a point A such that W is equal to how much it is given? 3 kilonewton per meter now. So by using the data, we have to draw the shear force and bending moment diagram for the cantilever beam. Okay, shear force diagram now. The shear force at B is equal to already we confirmed it is equal to 0 only. That is FB is equal to 0 now. Since there is no intermediate force portion there where other forces are acting now, hence it is varying continuously up to C position now. So we can take the shear force at C directly now. That is FC is equal to, generally it is treated as the area under this curve now. It is in the form of, here it is given triangle now. Here it is equal to 0, it is L, it is equal to W. The area under this curve is equal to the area of the triangle, half into base into height, or it is also equal to W into L by 2 now. Okay, from this relationship we got to, it is equal to 6 kilonewtons. So, from this take here 6 kilonewtons. From B it is a 0. Just draw continuous lines like this to point D. This curve is called here now parabolic curve because it is a proportion to the square of the distance from the free end. Now, bending moment diagrams. Here the bending moment diagram, it is since it is a positive, we have to take upward direction with respect to the base. For drawing bending moment diagrams, again draw lines downward direction to represent the length of the beam. Since the bending moment diagram is negative for the cantilever beam, the bending moment at B is equal to 0. At A is equal to, just we can take it as MA. It is equal to total force. Total force is equal to how much we have taken? W into L by 2 we have taken. But where it is acting now? At the center of gravity of the triangle from its base. That is from A, it is at a distance of L by 3 now. This is a point of application, the force from the base now. It can be simply written as WL square divided by 6 now. So W is equal to, we have taken 3 now. That is 3. L is equal to 4 square divided by 6. So it is also equal to now 3 into 4 into 4 divided by 6. Here 2 ja, it is equal to 8 kilonewton meter now. So you take 8 now. Here at B is equal to 0. 8 kilonewton meter means you have to take as per the suitable scale now. Draw vertical and downward directions. Assume 1 kilonewton is equal to 10 mm. That is 80 mm. You have to take it downward directions. Okay, join these 2 points by using smooth curve now. This curve is called here now parabolic curve. Sorry, this curve is known as cubical because the bending moment is proportional to the cube of the length of the beam. Here another problem. A cantilever beam of 2 meters span is subjected to a gradual varying load from 2 kilonewton per meter to 5 kilonewton per meter as shown in figure. Draw the shear force and bending moment diagram for the beam now. Here if you observe this beam now, this is known as the air simple supported beam. Here one end is fixed. At one end it is having 2 kilonewton per meter. Other end is 5 kilonewton per meter now. That means if you draw the lines now, here in the state, that is the beam is subjected to the combination of uniformly distributed load as well as the gradually varying load. Hence, when we are now considering the forces, we have to consider the uniformly distributed load at the same time gradually varying load. Here the given data in the problem is the length of the beam is equal to 2 meters. Given the gradually varying load, that is the load at A is equal to, is given the load at A is equal to given 5 kilonewton per meter. The load at B is given 2 kilonewton per meter now. This load may be assumed, split it into uniformly distributed load of 2 kilonewton per meter, because here if you draw the lines, this load is called here now, this load is called uniformly distributed load. It is equal to 2 kilonewton per meter, and gradually varying load is given here. If you out of 5, if you remove 2 now, the remaining is here 3 now. That is, we can take at A is equal to 3 kilonewton per meter, at other end is equal to 0 now. Now the shear force diagram for this beam is represented in B now. Here the load, the shear force here at this point is given by, that is nothing but at B point, it is equal to 2 kilonewtons is given now. Here 2 kilonewtons, and shear force at A is equal to, here the shear force at this point is equal to, because we can take it as a combination of at FA, B is equal to W into X for the uniformly distributed load, and for this one now half into W2 into X now, because this is nothing but for the gradually varying load now. It is for the uniformly distributed load now. When X is equal to 0, that nothing but at Bn now, because we are measuring the distance with respect to the free end now. When X is equal to 0 means the shear force acting at free end is equal to 0 now, because it is not the point flow now. It is nothing but distributed over entire its length, and moreover it is a combination of uniformly distributed load and gradual load. So by using this equation, when X is equal to 0, the FB is equal to 0 now. The shear force at A is equal to, that is FA, that is in this case W1 is equal to, we can take it as 2 now, W2 is equal to 3 now, X is equal to length of the beam, it is equal to 2 now. By substituting its values in this equation now, we can take it as 2 into 2 plus 1 by 2 into W2 is equal to 3 into 2 now. So it is equal to how much it is now? 7 kilonewtons now. So here in upward 7 kilonewton force is there now. At other end it is equal to 0. Because of this force, it is acting downward direction with respect to the point A, that fixed end. So This shear force is treated as positive. Hence, in order to draw the shear force diagram now, from B draw a line vertically downward directions. Again from A, one more vertical down direction. This parallel line is representing the length of the beam now. At your convenient distance, draw horizontal lines to represent the length of the beam. At B is equal to 0. At A, it is equal to 7 kilonewton force is there now. But it is a varying on the length of that is square of the distance. Hence, join this point B with the D where we represent a 7 now by smooth curve here like this. This curve is here it is called parabolic curve. Bending moment diagrams. Here the bending moment diagram is shown in here figure now. In C. Because the effect of the bending with this force is bend the beam in the form of convexity at the top. That is treated as a arcing effect. It is a negative. Hence, it should be always downward direction with respect to the axis of the beam. So, you have to represent the axis here horizontal lines like this now. Now, the bending moment at A is equal to, the bending moment at B is equal to 0. Already we got it now. The bending moment at A is equal to, for simple supported, for uniformly distributed load, the bending moment is equal to MB. It is equal to, that is the total load, that is the W1X, it is the total load, but it is acting at the center. So, we can take it as by 2 now. Again, already we have taken it the combination of uniformly distributed load as well as the gradual varying load. So, again we have to determine the bending moment created by the gradually varying load, which is equal to, total load is equal to W2 into X into half, because in nothing but area of the triangle we are taking this above it now. It is equal to 3, nothing but L by 2 now. It is equal to 1 by 2 into W into X. But it is acting at a distance of X by 3 now. That is center of gravity lies at the height by H by 3 from its base now. That means if you consider from this distance, here it is equal to X by 3 now. So, here now, by using this equation now, MA is equal to minus of, when you are substituting X is equal to L now, minus of W1 L square by 2, minus of W2 L square by 6 now. From these relations now, we got on substituting W1 is equal to N now, 2, W2 is equal to 3, X is equal to 2, and substituting the values 2 into 2 square by 2 plus 3 into 2 square by 6. Since these are all are negative only, it is equal to minus of 6 kilonewton meter now. Hence, draw vertical lines in downward directions 6 kilonewton meter. So, it is representing as 1 kilonewton is representing just 10 mm. They draw the 60 mm length in downward directions. Just join these points by smooth curve. This curve is following cubic law now. Okay, this is the effect of shear force and bending moment diagram of the beam. We need to subject it to gradually varying load now. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.